Buenos días. Mi nombre es Gonzalo Tancredi y estoy en representación del Comité Científico y Comité Organizador Local de esta Reunión Regional Latinoamericana de Astronomía de la IAU. En primera instancia, bienvenidos a todas y todos, bienvenidos a todas y todos. Welcome to everybody. Lo hago así porque, bueno, como voy a explicar más adelante, los tres idiomas que utilizaremos en esta conferencia son el español, el portugués y el inglés. En primera instancia, bueno, agradecerles por estar aquí en esta reunión latinoamericana de la IAU. 28 años después de la anterior que organizamos acá en Uruguay en el año 1995. Han pasado muchas cosas y después capaz que comento un poco más. En particular, tuvimos en los últimos años la pandemia que hizo que esta reunión, que iba a ser organizada el año pasado, tuvo que posponerse un año. Queremos agradecer en primera instancia a la comunidad latinoamericana de astronomía que en la última reunión en Antofagasta apoyó la propuesta de organizar esta conferencia aquí en Uruguay. Como todos ustedes saben, nuestra comunidad de astronomía en Uruguay es bastante pequeña y para nosotros ha sido, como lo fue en el 95, un gran desafío. Así que les agradecemos a todos y todas por haber apoyado esta propuesta. También queremos agradecer a la Unión Astronómica Internacional. En representación aquí tenemos a Daniela Lázaro, vicepresidenta de la IAU, por haber también apoyado esta reunión. A la Intendencia de Montevideo, que generosamente nos facilitó estas instalaciones, que también hubiera sido casi imposible organizarlo sin este apoyo de la Intendencia, y en particular al Planetario Municipal, que jugó un rol importante en toda esta gestión. A la Universidad de la República, nuestra máxima universidad aquí en Uruguay, la Universidad Pública, y en particular a la Comisión Sectorial de Investigación Científica, y a la Facultad de Ciencias, que aquí tenemos a nuestra decana, la doctora Mónica Marín, en representación de la UDELAR. El rector y varias autoridades en este momento están de viaje por China, creo que es, que tenían una gira bastante importante para lo del AR en estos días. Al Programa de Desarrollo de las Ciencias Básicas, PDCIVA, que también apoyó esta actividad, y a la Universidad Nacional Autónoma de México, que nos apoya con la edición de los proceedings de esta conferencia. Queríamos manejar algunos números para que ustedes sepan de qué actividad estamos organizando. Tenemos registrados más de 400 personas, 410 participantes de 19 países diferentes, obviamente más del 80% de América Latina. 350 son del exterior, o sea que ya ven ustedes que es una conferencia mayoritariamente no de uruguayos, sino de gente de toda la región. También nos parece muy grato para nosotros que el 53% de los participantes son estudiantes de grado y de posgrado, o sea que hay una participación muy activa de los jóvenes investigadores en astronomía en esta reunión. También nos parece importante remarcar que, pese a la disparidad de género que hay en nuestra región, en las áreas de las STEM, de las ciencia, tecnología, ingeniería y matemáticas, el 40% de los inscriptos son colegas del género femenino, son mujeres, y eso también se ve reflejado, y en particular por la iniciativa del Comité Científico, que la mayor parte de las charlas, el 55% de las plenarias son a cargo de colegas mujeres. Entonces creo que estamos actuando la comunidad en la línea de tratar de mejorar los números de paridad de género en nuestra área. Para nosotros ha sido un desafío muy importante organizar esta conferencia. Sabemos las condiciones económicas difíciles que tienen países de la región, nuestros vecinos Argentina. Tuvimos que diseñar algún mecanismo para poder facilitar la venida de cantidad de colegas de Argentina, que en otras condiciones quizás hubieran sido bastante más. Hay muchos países de la región que lamentablemente no pudieron concurrir, viendo un poco los números, capaz que eso lo revisamos más en la asamblea, pero tenemos muy pocos participantes del Caribe, de América Central, de Venezuela. Pero bueno, pese a esas difíciles condiciones económicas, logramos organizar esta reunión. Para no extenderme mucho, algunos agradecimientos finales. En primera instancia, al comité científico, que quizás, digamos, cambiando un poco la tradición que tuvimos en otras instancias, optamos por que las asociaciones latinoamericanas de astronomía de cada uno de los países designaran a representantes para integrar este comité científico. Entonces tenemos integrantes de los principales países de América Latina, algunos con asociaciones constituidas, y creo que es una tradición que debemos apoyarnos muchos más en las asociaciones científicas que tienen cada uno de los países. El trabajo del SOC fue bastante difícil, tuvimos más de 550 propuestas de charlas o pósters, de las cuales tuvimos que seleccionar unas 150 para charlas, más precisamente 159, sobre una cantidad bastante grande, más de 250 propuestas de charlas. O sea que fue un trabajo bastante difícil el del SOC, tanto para elegir las charlas como especialmente elegir las charlas plenarias, tratando de tener una, como decíamos, paridad de género, pero también una distribución equitativa a nivel regional. Y finalmente, y quizás el más importante, el trabajo que ha desarrollado el LOC, el comité local. Quiero agradecer especialmente a Cecilia Mateu, que más que co-chair fue chair de esta reunión, y a Juan José Dons, que es el chair del comité científico local. Yo les recordaba al inicio, en el año 1995 organizamos la primera y única hasta ahora reunión latinoamericana de astronomía aquí en Montevideo. En aquel momento éramos solamente 2 científicos profesionales, Julio Fernández y yo, y una cantidad de estudiantes, en un número quizás diríamos de un puñado de estudiantes muy interesados, algunos en su etapa de posgrado, pero muchos todavía en la etapa de grado. Hoy en día eso ha cambiado, quizás menos de lo que esperábamos. Hoy en día tenemos unos 6 astrónomos profesionales trabajando en Uruguay, pero un conjunto bastante importante, y muchos están aquí, de colegas uruguayos que se formaron aquí y que luego continuaron sus carreras académicas en el exterior, a los cuales nos han ayudado mucho en la organización. Y quizás un grupo de más de 40 estudiantes de grado y posgrado que han venido trabajando. O sea, hemos tenido un crecimiento, quizás no similar a otras comunidades, pero un crecimiento importante que ha hecho que los más veteranos ya podamos delegar en otros la organización de esta reunión, y en particular pensar que, bueno, capaz que dentro de, no sé si 28 años, pero un número un poco más bajo, podamos tener una nueva reunión latinoamericana de astronomía aquí en Uruguay, ya no organizadas ni por mí, ni por Cecilia, ni por Juan José, sino por los más jóvenes. Así que bueno, con esto quiero terminar. Agradecerles entonces a todos y a todas por la participación, y le voy a dar paso a Mónica Marín para que en nombre de la Facultad de Ciencias y de la UELAR haga unas palabras de apertura.
Muchas gracias, Gonzalo. Bueno, muy buenos días a todas, a todos. Un gusto enorme recibirlos en nuestro país, en Montevideo, y de parte de, como decía Gonzalo, de la Universidad de la República y la Facultad de Ciencias, un abrazo de bienvenida, deseando que sea esta reunión muy fructífera. Y quisiera especialmente referirme a los estudiantes de aquí y que han venido desde el exterior. Los congresos siempre son una oportunidad, cada uno es una oportunidad única de acercarnos a las personas que tienen trayectoria o los que están recién empezando su carrera de investigadores, no importa, es una oportunidad única para que se acerquen, conversen, interiorizarse mucho más a través del relacionamiento humano con la disciplina, con la experiencia, con las trayectorias. Así que la primera y fundamental recomendación, anímense. A veces a los uruguayos nos cuesta un poco ese abordaje primero, pero bueno, que lo hagan y que van a ver que va a ser algo muy fructífero también de esta reunión. Muy contenta con estas cifras también de la representación de las mujeres que ha venido creciendo en la disciplina, así que también muy contenta con este primer pantallazo que nos ha brindado Gonzalo. Bueno, a todos los visitantes, a todos bienvenidos y que sea lo mejor para esta reunión para todos. Gracias.
Bueno, antes de algunos anuncios, queríamos agradecer nuevamente a la Intendencia de Montevideo, en representación aquí del director de Artes y Ciencias, el arquitecto Baltasar Brum, por habernos cedido generosamente estas instalaciones y, como decíamos, también el agradecimiento a la Dirección de Cultura, al Planetario Municipal. Así que muchas gracias, Baltasar. Sabemos que es un día bastante especial aquí en la Intendencia porque creo que se conmemoran los 4 años de esta gestión de gobierno y entonces, 3 años de esta gestión de gobierno y entonces iba a haber algún acto en uno de los salones de aquí cerca y por eso muchas de las autoridades de la Intendencia estaban presentes ahí. Para ir cerrando esta parte introductoria, algunos anuncios. Como decía, en primera instancia, hay 3 idiomas oficiales de esta reunión, que son el español, el portugués y el inglés. Las presentaciones pedimos que pueden ser en cualquiera de estos 3 idiomas, pero generalmente lo que hacemos es, en caso que, por ejemplo, sea en español, poner las slides, las diapositivas, en el idioma inglés. O lo mismo si es en portugués, ponerlas en inglés, o si no, al revés. Pero pueden usar indistintamente estos 3 idiomas. Entendemos que al hacerla en nuestros idiomas nativos, le damos más fluidez, le damos más posibilidades de intercambio y para los jóvenes, que para muchos será quizás la primera presentación, les quita un poco de presión al poder hacerla en su propio idioma. Después también algunos otros anuncios. Van a ver que en la página web de la reunión hay una pestaña que dice Advertisements, anuncios, en la cual van a ver eventos, por ejemplo, próximas conferencias o también ofertas de trabajo y ofertas de becas, así que les pedimos que los chequeen ahí. Y se da que esta semana hay algunas actividades culturales que les pueden interesar a muchos de ustedes. Las vamos a ir poniendo en una cartelera que pusimos ahí adelante. En particular, creo que, porque algunos ya han consultado, en el día de hoy hay un concierto de un famoso músico uruguayo, Rubén Rada. Queremos hacer el anuncio porque es un concierto en apoyo a una institución, vecina nuestra, que es el Instituto Pasteur de Montevideo. Entonces es un concierto en el Teatro de Verano de Rubén Rada en apoyo al Instituto Pasteur. Y después la Banda Sinfónica Municipal hace un concierto basado con la obra de Gustav Holst de Los Planetas, que va a estar en el Teatro Solís, el principal teatro municipal de aquí de Uruguay, y en otras instalaciones van a ver ahí en la cartelera. Así que los invitamos también a acompañar estas actividades culturales que están, bueno, directamente relacionadas. Y si culminamos las gestiones, el día viernes vamos, quizás ya muchos de ustedes al ingresar por la Rambla de Montevideo vieron un cartel que dice Montevideo. Bueno, a partir del viernes, porque justamente es el cambio de mes, va a estar pintado con referencias a la astronomía y va a estar presente por un par de semanas ahí con referencias a la astronomía. Vamos a hacer un anuncio más sobre la fecha, capaz que para invitarlos a que nos ayuden a completar, a pintar este cartel. No sé si había algún anuncio más para hacer por parte de la organización. Solamente recordarles que suban las charlas lo antes posible, no más allá del día antes de su presentación. Así que bueno, con esto damos por abierta esta 17ª Reunión Regional Latinoamericana de Astronomía. Gracias a todas y todos. Doy paso a Cecilia Mateu, que va a ser la chair de la próxima sesión.
Bien. Bueno, buenos días. Les doy la bienvenida entonces a la primera sesión plenaria de la mañana de hoy, que va a ser sobre el tema de formación y evolución de galaxias. Y para mí es un placer especial presentar a la primera conferencista de la mañana de hoy, que es Yara Jaffé, que nos va a hablar sobre la evolución de galaxias a lo largo de la telaraña cósmica.
Gracias, Cecilia. Y muchísimas gracias a los organizadores por haberme invitado a hablar aquí hoy. Es realmente un placer estar aquí, ver a tantos amigos del pasado que no veía hace mucho tiempo. Y también un honor poder abrir esta conferencia, esta LARIM, en Montevideo, que es una bellísima ciudad. Me voy a cambiar a inglés, pero dejé las láminas en español. Y cuando me hagan preguntas, me pueden hacer obviamente preguntas en español, en inglés, en portuñol, o lo que quieran. So, today I'm going to give you a review on some aspects about how galaxies evolve throughout time and space. In particular, I'm going to talk about how galaxies transform as they migrate along the cosmic web from low-density environments towards high-density environments. Sorry. Okay, so to give you a brief, very general introduction, we know that galaxies come in a very wide variety of shapes, colors, sizes, and properties. And no galaxy is like another. They're all different. But we can look for common properties to try to group them in different classes and try to understand different possible evolutionary paths for galaxies. We've been doing this for a century, more or less. So the first person that tried to classify galaxies, do taxonomy for galaxies, was, Edwin Hubble. And he came up with what we call the Hubble fork, where, as you know, we have here elliptical galaxies, lenticular or S0 galaxies, and the ordinary spirals like our own, with a bar or without a bar. And then here to the right, we have the kind of weirdos, the irregular galaxies, that are also, of course, an important part of the universe. And Of course, galaxies have a lot of specific characteristics, but very broadly, we can classify them in two main types. One type that is old. Ooh, sorry, I'm getting used to this. So one type that is old, let me switch hands, which is basically composed of elliptical and lenticular galaxies. And these galaxies are characterized for not having much gas, so they cannot form stars because they don't have material to form stars with. And morphologically speaking, they tend to be more spheroidal-like, okay? And because they're old, they don't form new stars, they look red, okay? Because the stars that are already in those galaxies have aged and they look red. On the other hand, we have spiral galaxies, which are much younger. We call these the young galaxies because they have a lot of gas, which makes them form new stars. And the new stars dominate blue light. So these galaxies look blue. And I say that there's two classes of galaxies, broadly speaking, because if we look at the color distribution of galaxies, we actually see a bimodality. So this is a color mass diagram. And we see that if we only look at color, if we only look at color, we have a bimodality. We have many galaxies lie here on the red sequence, and the rest of the galaxies are in this blue cloud. So basically, there's not a lot of galaxies that are in between these two types. So this is the first clue of galaxy evolution. So I'm going to give you several clues, and we're going to start to build a scenario of how galaxies evolve. And another thing of this plot is that we see that the most massive galaxies in the universe, so this is 10 to the 11.5, are always these huge elliptical dead galaxies, okay? So to find star-forming young galaxies, generally we have to look at lower masses. Now, a key aspect about galaxy evolution is where galaxies live. What's the environment of galaxies? So we have to go look at the large-scale environment of galaxies. So this is the cosmic web. You might have seen this image a billion times, for sure. This is the Millennium simulation. So this is the distribution of matter, specifically dark matter, in the universe, as simulated in a computer. And we have here different components. So for example, the highest density parts of the universe are, of course, these clusters of hundreds or thousands of galaxies grouped together that can weigh as much as 10 to the 15 solar masses. These are really monsters, the most massive virialized structures in the universe. And these clusters are being fed from galaxies that come along in little groups, alone, or sometimes through cosmic filaments, okay? And these filaments also separate huge areas of empty space called cosmic voids. So galaxies distribute in this cosmic web. And the interesting thing is that we've been finding and confirming through time that the different types of galaxies that I mentioned really prefer different environments. So the old galaxies prefer to live in clusters in the densest regions of the universe, while the young galaxies prefer to live in calmer, quieter, countryside-ish places of the universe, okay? So this is summarized by this plot. This is a famous plot by Dressler in the 80s, where he plots the fraction of different galaxies as a function of galaxy density, okay? And you can see that elliptical and lenticular galaxies, these two here, are more common in high-density environment, but spiral and irregular galaxies are a lot more common in low-density environments. And this is at redshift 0. This is in the local universe. If we go and look at galaxies at higher and higher redshift, as we continue to do with bigger and better telescopes, we find that in the past, there were a lot more spirals than there were now, okay? This is look-back time as a function of fraction of galaxies. So in the past, there were more spirals than now, and this behavior is the opposite of what's been happening to, for example, lenticular galaxies. So this is a second clue. Perhaps these galaxies are being transformed into these ones, and that's why one is less common now than before, and the other one is more common. Now, we know now that the most likely explanation of the evolution of galaxies is that these guys here, these young, blue, disky, or irregular galaxies, somehow convert into these red and dead, and sometimes more massive galaxies, okay? And in this talk, I want to dedicate this talk to try to explain how. How does this happen? How to kill a galaxy could be another name for my talk. So the first thing to consider is that there are two broad mechanisms, okay? Nature and nurture. Let's see what I mean by that. So this is another famous plot by Peng et al. 2010, where we have stellar mass on the x-axis, so massive galaxies here, low mass galaxies here. On the y-axis, we have galaxy density. So the cores of galaxy clusters would be up here, and empty spaces of the universe are here. And the color bar indicates, in each pixel, this plot contains observations of thousands of galaxies, okay? We are looking at the fraction of old galaxies, passive galaxies, red galaxies, however you want to call them, non-star forming galaxies, okay? And we see that if we focus on the x-axis, for all massive galaxies, anything above 10 to the 11, everything is red, which means that the probability of a galaxy to be quenched or old is extremely high if the galaxy is massive. It doesn't care about environment. If you have a massive galaxy, it will be dead. However, if you look below 10 to the 11, environment plays a huge role. It really depends where you live to determine whether you're quenched or not. So this is why I say that galaxy evolution is really governed by two things. Nature, which refers to the internal properties of galaxies, in this case, galaxy mass, and nurture, which refers to the environment in which the galaxy is embedded. So starting with nature, so this talk is really not focused on nature, but I feel I have to mention it. So the natural ways a galaxy can quench or can stop forming stars is basically through internal mechanisms. And examples of these internal mechanisms include, for example, a supermassive black hole in the center of the galaxy that expels a lot of material at high energies outside the galaxy. So in this chart here, I show what is called the baryon cycle of galaxies, which shows that for a galaxy to form stars, it needs to accrete gas from the web, okay? That gas is then going to be forming stars in the disk of the galaxy. But if you have an active galactic nuclei in the center throwing gas away, it's going to create a feedback. It's going to affect the amount of gas that that galaxy can accrete, and it's going to prevent it from forming more stars. Another source of feedback can be star formation itself. When you form stars and you have a lot of supernova explosions, if the galaxy is not capable to attract that gas back, it will lose a lot of gas through feedback. So that's nature. How about nurture? Well, if we look at the breakdown of where galaxies live in the cosmic web, we see that actually the vast majority of the universe is empty. Okay, voids dominate the universe in terms of volume. But if we look at where the mass of the universe is, we find that most of the mass in the universe is in the structures, in filaments most of all, walls, and also these nodes, which are the galaxy clusters. Okay, so while the universe is empty, it's actually the distribution of the mass is, of course, tracing these structures. Now, these structures are not static. They evolve with the universe. So this is another cosmological simulation showing how the structures evolved from the early stages of the universe, after the Big Bang, to present times. And what we see through observations as well as simulations is that these massive galaxy clusters grow and continue to grow through the accretion of groups and galaxies from filaments, okay? Through this kind of strengthening of the cosmic web. So from the galaxy's perspective, the environment of one galaxy is not static. If I'm a galaxy that was born a long, long time ago, my environment will always go from a lower density region of space to a higher density region of space. Why? Because of gravity. I will always be attracted to the nearest structure near me. Okay, so let's think from the point of view of a galaxy falling into a cluster. So this is a PowerPoint-made animation. Sorry, it's not very fancy. So this is a galaxy in the outskirts of a cluster, really, really far from a cluster. This would be a cluster center, and this yellow thing here is filaments identified in this simulation, okay? So if that galaxy is in a void, that galaxy is going to be accreting gas from the cosmic web and forming stars. Now, as that galaxy falls to its nearest structure, in this case it's a filament, what happens is that the supply of gas, this accreting gas, is going to be cut off. I'm going to cut off that supply of gas, and the galaxy is essentially going to start to starve, in the sense that it's not going to have material from which to form new stars. So it's the beginning of the death of that galaxy. We say that that galaxy starts being processed or pre-processed before it finishes to die when it falls into the cluster. So the last stage is that the galaxy falls into the cluster, and the cluster, as I'm going to show you in a second, is a much harsher environment. Clusters can contain thousands of galaxies, hot gas, a huge gravitational potential, and this makes the galaxy completely dead after a certain amount of time. So that's basically what we think happens to galaxies, in a summary of a lot of, a simplification of a lot of more complicated works. But the main point I want to make is that the ability of a gas to keep its youth is to form stars, and it can only form stars if it has gas from which to form those stars. Okay, let's look at what happens to galaxies in dense environments. What are the environmental effects that can quench galaxies? Again, there's two main categories of environmental effects. One category is gravitational interactions, and the other category is hydrodynamical interactions. In gravitational interactions, gravity affects everything that has mass, right? So dark matter, stars, gas, everything is affected. But in the hydrodynamic case, only the gas component of the galaxies will be affected. So we're going to see what I mean in a second. Let's start with gravitational interactions. I'm sure everybody here, even your grandparents, will have probably seen a Hubble image of galaxies merging, because they're very pretty. I put here some of them. These are, typically two galaxies that we can clearly see, and they're in the process of interacting, okay? And when they're interacting, lots of things can happen. If these galaxies have gas, the gas compresses, it forms a lot of stars, and then it kind of dances around until it settles into a big, massive galaxy. And this is what we see here. These are simulations of two spiral galaxies merging, and you can see that by the end, if you merge two spiral galaxies, the outcome is going to be a big elliptical galaxy. So here we figured out one way to make big fat ellipticals. You fuse two spirals together. Okay, we've solved one problem. The thing is that the merger fraction, so the amount of merging galaxies we see in the local universe, is actually pretty low. It doesn't seem to be that common for galaxies to merge nowadays. It was a lot more common in the past. The higher the redshift we observe, the higher the merging fraction that we get. So mergers are important, but they're not the whole story, okay? It cannot be the whole story. What other kind of gravitational interactions? Well, I told you clusters are the largest virialized structures of the universe, so it makes sense that they have some kind of gravitational effect on galaxies. And they do. In galaxy clusters, this is a famous James Webb, the first James Webb image. It's a beautiful, massive galaxy cluster with these gravitational arcs and everything. You see here in the middle what we call the BCG, the brightest cluster galaxy, which dominates the gravitational potential of the galaxy. And the thing is that all these galaxies in the cluster, so all these yellow fuzzy things are cluster members. If you have 1,000 of them, they're going to be traveling, they're going to be in that cluster environment, traveling at very high speeds. It can be typically, 1,000 kilometers per second traveling in that cluster. So that means that it's not really easy for galaxies to merge because they're going too fast. When you go that fast, you don't really fuse with one another, you just fly by, okay? But an accumulation of those very high-speed flyby encounters can also affect galaxies. It can puff them up, they can lose mass, they can transform morphologically, and they can eventually quench as well. But this kind of affects, because they're cumulative, they take a longer time scale. They're kind of a long process that quenches galaxies. The galaxy has, leaving the stars unaffected. So the stellar disk of the galaxy is untouched, but the gas is blown away. And you get this kind of trails of gas trailing behind the galaxy as the galaxy moves. So in this case, these tails of gas, so here blue is gas and red is stars, the gas trails are always going to be in opposite direction of movement, okay? And the thing is that at some point, this cartoon is an exaggeration, but at some point, the galaxies are going to be left without gas, they're not going to form stars, and eventually, a little bit later, they're going to be red and dead again. So environment is hard on galaxies. They can die in many ways. And regarding RAM pressure stripping, there's a very easy way to characterize it analytically. So the RAM pressure stripping formula is super simple. We have here the RAM pressure, which is proportional to the density of the ICM. Okay? The denser the gas is, the more stripping you will have, and the velocity of the galaxy. You can imagine if the galaxy is traveling very fast, it's like it will feel a stronger wind. Okay? And if this RAM pressure supersedes the ability of the galaxy to retain its gas, so basically its self-gravity, then you will lose the gas. That's the RAM pressure condition. If the RAM pressure is higher than your self-gravity, you lose the gas. And of course, this starts to happen at the outskirts of the galaxies where the self-gravity is weaker, and it will end up happening at the center of the galaxy, where the galaxy is a little bit more able to retain its gas. So I just want to kind of say that there's a lot of environmental mechanisms that can affect galaxies. This is a cartoon stolen from a collaborator, Airi Chung, where she puts all these different, we have harassment, tidal truncation, thermal evaporation, RAM pressure stripping, gravitational interactions. Many things can happen to galaxies. But in this talk, I'm going to focus a lot on RAM pressure stripping, which is the one that I just told you today. And the justification for that focus is because we think it's one of the most rapid and fundamental things happening to galaxies in clusters. Okay, these are some simulations of RAM pressure stripping at play. Okay, so on the left we have here, this green thing is gas, and the white contours are the stellar body of a galaxy. And what the simulators do is that they take a galaxy, they put a disk, of stars, a disk of gas, and they put it in what they call a wind tunnel. Imagine a tunnel, and then you switch on the fan, and you blow away all the gas that the galaxy has. And what that does, according to the Ram pressure stripping criteria, is that it first starts stripping the outskirts of the galaxy, and then it eventually kind of eats in the gas until the center. And in this process, you have all these beautiful tendrils or tentacles of material that sometimes can clump together in higher density clumps. And it's predicted that it can even form stars outside the galaxy. So these are candidates where star formation can happen outside of galaxies, okay, which is cool. And on the right-hand side is another plot from simulations where you see that this stripped gas is predicted to be multi-phased. We expect to see it in different wavelengths. And in different wavelengths, we will see different behaviors from star formation, etc. So we can see it from X-rays, H-alpha, H1, molecular gas, etc. So this is kind of like from the simulations point of view. And if we go to the observations, this is a review, so I'm presenting here the kind of like the historical, most outstanding first evidence that Ram pressure stripping is ubiquitous in clusters. So this is work by Aire Chung, the same one that did the cartoon, in the Virgo cluster, where you have here the X-ray emission of the Virgo cluster in yellow, and these are the galaxies in the Virgo cluster observed in radio, in 21 centimeters, which means that we're observing the neutral gas that helps forming stars. And if we look at some of these galaxies a little bit closer, at these 4 examples here, the white lines, the contours, are the H1 gas, and the optical image behind represents the stars, okay? You can see, I don't know if in the screen you can see, but the stars are basically unaffected disks. Nothing is happening to the stars, but the white contours are clearly disturbed and being pushed away by the intercluster medium, okay? And you can kind of guess how these galaxies are falling into the cluster. This one, for example, is going towards the cluster in this direction, so the cluster is pushing the gas in the opposite direction, okay? Since then, so that was 2009, since then there's been a lot of papers in the literature. I didn't attempt to do a complete review of everything that's been done. These are just some examples that I like of detections of this process in different wavelengths, okay? So to date, we've observed Ram pressure stripping in the dust content of galaxies, as I show here there on the left. We've observed it in X-rays with spectacular long tails. We've observed a lot of it in H-alpha. H-alpha gives you the ionized gas in these tails, and typically this gas is being ionized by stars forming in the tails. These are very recent HST images that we got of a jellyfish galaxy in the optical, so we can see all those blue dots that are star-forming pockets, and also in CO, okay? So ALMA observations of these galaxies show this kind of multi-phase stripping. Now, because of their morphology, these galaxies have been called jellyfish galaxies. It's obvious. They have these really long tails, and unlike galaxy mergers, the tails are only to one side. Typically in mergers, you have 2 tails. band optical image reconstructed from News Data Cube. And this is an H-alpha image. So if you have H-alpha images, it's super easy to detect them. But what's cheap in astronomy is not H-alpha imaging, it's optical imaging. So we tend to look for them in the optical and then follow them up in other wavelengths. And because we look for them in the optical, we find that about 20% of optically young galaxies have these jellyfish tails, okay? But we estimate, considering this and the work in other wavelengths, that actually all young galaxies falling into clusters must experience at least some degree of stripping. And I'll show some other results that prove that. The other interesting thing is that recent works looking at much less massive structures, like galaxy groups, can be talking about, I don't know, 20 galaxies in a group or 10 galaxies in a group, much lower mass systems, also have jellyfish galaxies. They're not as spectacular as the ones we see in cluster, but they exist, which means that this process maybe is not so rapid in groups, but it still exists. It still affects galaxies. So it's a process that we cannot ignore. It's there, and we have to account for it. So one of the things that we want to do is understand how effective is run pressure. So for a long time, we've been using a specific kind of diagram that is called the phase space diagram, where you have the distance from the cluster center in the x-axis and the relative velocities of the galaxies relative to the cluster mean on the y. So if the cluster is virialized, the galaxies, which are the crosses, will locate in this kind of trumpet shape, okay, below the escape velocity. And a galaxy falling from far away in the cluster will approach the cluster center gaining speed as it goes through pericenter, then it goes to the other side, losing velocity, and then it kind of keeps falling back and forth and virializing and losing velocity as it does that. So we can use these diagrams to infer statistically the orbital histories of galaxies in clusters. And we've been doing that, as I said, for many different things, not only to study run pressure. And it's a very effective way to do it. So basically, galaxies that are here have recently fallen into the cluster, and the ones that are close to this triangle, we can say that statistically, they've been in the cluster for a lot longer. Of course, there are projection effects. That's why this has to be done in a statistical way. And the other cool thing that we've been doing with these diagrams is that we can use them to add in information of the different physical mechanisms affecting galaxies in clusters. So in this illustration, I show you how run pressure stripping is expected to act. So when the galaxy crosses a certain distance from the cluster radius, the intergalactic medium is dense enough that it will start stripping the galaxy. And at the same time, the velocity of that galaxy will go up. And velocity was the second parameter. So we can predict where these galaxies are going to be stripped and try to look there. And this is what we've been doing. I'm going to show you the older work where we did this. On the left side, we have simulations of stripping predictions in phase space. So here, the red and yellow, orange regions are where we expect stripping to have, we don't expect any galaxy to have gas anymore in that region. And on the right, we have observations of galaxies in a cluster with the blue dots indicating which ones have gas, okay? And we can see that it resembles a lot, the galaxies that have gas are all in this region where the simulations predict that galaxies haven't been stripped yet, so the blue part of this diagram. And what this means is that the stripping process is actually really fast. When you cross the cluster one time, the first passage to the cluster is already removing the gas from galaxies to make them undetectable by this particular survey. And well, this has been confirmed in many ways. I don't have time to go through it. But another thing that some people have been doing is to try to constrain with numbers the duration of this phase, of the stripping phase. And the cool thing about jellyfish galaxies is that the tails provide an additional piece of information about their orbits. So if you combine phase space information with tail directions, you can really know if they're on first infall or coming out or whatever. So this is an example, a recent example by Roberts et al. 2020, where they looked at the tail directions in the Coma cluster for jellyfish galaxies, and they found that most of them have tails pointing away from the cluster. So here, a large angle means that the jellyfish galaxy angle is this one, okay? So the tail is pointing directly away from the cluster center. And this means that at least in the Coma cluster, most of these galaxies are falling in for the first time, which corroborates our previous findings in phase space. And well, very recently with a master's student, Vicente Salinas, we actually put numbers to this. So we compared the observations with simulations and some MCMC analysis, and we actually come up with these numbers. So we think that the galaxy tails start appearing a little bit beyond the virial radius of the cluster, and they disappear just a little bit after the galaxy has crossed pericenter, about 600 megayears after. Of course, this will depend on galaxy mass, cluster mass, blah, 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 but this is kind of like a first attempt to try this because we're still building this large statistical sample so that we can bin in many kinds of properties. Okay, finally, what effects does RAM pressure stripping have on the galaxies? There's been several important surveys with multi-wavelength data looking at what happens to galaxies when they strip. One of them is the Vestige project that is looking at H-alpha emission in the Virgo cluster. Another one is our GASP survey, which looked at hundreds of jellyfish galaxies, over 100 jellyfish galaxies in many different clusters, with this beautiful instrument, Muse, that basically gets you a data cube of galaxies where you can really dissect them. I'm running out of time, so I'm just going to show you, this is how the galaxies look in the optical, and if we look at the H-alpha in Muse, we really start looking at this tremendous amount of stripping. So the first thing that we did is separate the stars with the gas, and we can see that, again, the stars are untouched and the gas is completely detached. And the other thing we have with Muse is that we can see in each pixel of the image a spectra. So we have 90,000 spectra in an image. So we can look at different regions, and we confirm that in these knots in the jellyfish tails, we have star formation. So there's star formation occurring outside the galaxy. We also found in the centers of these galaxies, often there is an active galactic nuclei. And we also found some evidence of outside-in quenching. So in the outskirts of the clusters, we have spectral features that are consistent with post-starburst, which also tell us about how these galaxies are quenching from the outside in. One of the unexpected results of our survey was that we found a huge fraction of AGN in our sample. And this is unexpected because AGN are rare in the universe. So active galactic nuclei are between 3 and 8% in population, okay? And we were finding that most of our spectacular jellyfish galaxies had an AGN. And since then, we've been able to corroborate this result originally published in 2017, that RAM pressure is not only removing gas from the galaxies, but part of that gas is being funneled towards the center, activating the black holes. And to finalize, the next stages of what we're trying to do now as a community is to understand how galaxies are affected outside of clusters. We know that clusters definitely quench galaxies. We have understood pretty well, not everything, but a lot about cluster quenching. But we're trying to understand what about all those galaxies that arrived to the cluster already quenched? What happened to them? We expect over 40% of galaxies to have come to clusters in groups. So what's happening with them? I wanted to share this very recent plot from Paulo Lopez, from a colleague from Brazil, showing the fraction of star-forming galaxies as a function of cluster-centric radius, okay? And you can see that even at 5 virial radii, cluster galaxies are a little bit more quenched than field galaxies. But if you look at galaxies in subgroups or substructures, they're a lot more quenched. So this is what we call pre-processing, okay? And I'm running out of time, so I'm gonna skip this slide, and I'm gonna go to the future. What what are we looking into? So we're now building these large data sets. We really need to study this process statistically. And it's very hard, okay, because typically these things are done visually. So now we're relying on citizen science, for example, and also machine learning techniques. But we don't want to lose machine learning techniques blindly. We need to train them with data that we're confident. So we're starting with citizen science. There's several projects. This one is our own, Fishing for Jellyfish Galaxies, but I'll put here another example of galaxies in simulations. There's a bunch of citizen science projects that can help us build these huge samples so we can start understanding this better. And in terms of observations, I wanted to highlight a few things that, at least in Chile, are going to change this field significantly. The first one, I call it future, but this is actually ongoing. So there's the S+ survey. There's going to be S+ talks this afternoon, so you can hear more about it there. But the S+ is a small telescope PI'd by Claudia Mendes Oliveira in Brazil, and it has 12 different bands. So we can really use that to have a good characterization of galaxy morphology and environment. We also have Foremost coming to Chile. This is a huge spectroscopic facility, and actually with Chris Haynes here in the audience and myself, we're leading a Chilean project to use this instrument to target a lot of galaxies in the surroundings of clusters and try to understand pre-processing better. And Chris will talk about that, so I don't have to mention it. And also the Vera Rubin Observatory, or LSST, that is going to give us a very deep view of the southern sky. It's going to scan the whole sky in a few days, so you can do variability, you can do galaxy evolution, you can do many things with that. So that's another exciting thing coming in Chile. I ran out of time, so I'm just going to quickly give you the take-home message. So I hope I've convinced you that galaxy evolution is a complex process where the evolution of structure goes along with the evolution of galaxies. Clusters are very effective at killing galaxies. And we are still to understand what happens to galaxies before they enter clusters and how they're pre-processed in filaments and groups. So stay tuned. Thank you very much.
Okay, so any questions for Yara? Let's see. Emir?
Thank you, Yara. Very nice talk. I expect that the physics of ground pressure and yellowfish galaxies strongly depends on the gravitational potential of the cluster. So I'm wondering if the observations, current observations, the phase space diagram, or the fraction of yellowfish galaxies as a function of a cluster-centric radius would be able to say something about the nature of dark matter, or if dark matter is Mond, for example. I think the physics should depend on this, and observations could give us some information to constrain the nature of the gravity, let's say. Do you have some comments about that?
Yes, difficult question, but very good one. So phase space, obviously the virialization of a cluster depends on the dark matter potential. And missions like Euclid and things like that are going to be able to reproduce and populate many phase space diagrams in clusters, okay? And theoretical physicists that are not me, that I know, tell me that with different theories of gravity, for example, modifying gravity, you expect different shapes of the envelope of this phase space diagram. So it can be used as a powerful probe to study gravity, but at the moment we're limited by sample sizes and depths, and you need a redshift range and blah, blah, blah. So it will be done in the future.
Muy linda la charla, muchas gracias. Yo tenía una pregunta. Porque explicaste que la ramp pressure va a cambiar básicamente de galaxias azules a rojas, por esto que estás explicando, pero ¿qué hay de la morfología del cambio de espirales a elípticas? ¿Cómo se produciría ese cambio?
Muy buena pregunta, sí. Me alegro que lo preguntaras, porque fue una simplificación decir que ramp pressure simplemente convierte una espiral en una lenticular. Las lenticulares no solo son distintas a las espirales en el hecho de que no tienen gas, sino que tienden a tener bulbos más prominentes, ¿okay? Tienden a tener discos más gorditos, ¿okay? Son un poco diferentes. Entonces, ramp pressure solo no puede hacer eso. Tú necesitas otros mecanismos. Entonces, primero quitas el gas. Cuando quitas el gas, los brazos espirales se van a ir disolviendo, pero necesitas otros procesos cumulativos que vayan inyectando energía cinética al disco, engordándolo y también inyectando cosas al centro. Parece que ramp pressure sí puede inyectar cosas al centro, como dije, alimenta los huecos negros y eso también. Hay otras cosas, por ejemplo, cuando entras a cúmulos a veces se incitan la formación de barras. Las barras también pueden formar mayores bulbos, cosas así. Y harassment, el acoso de galaxias, también puede ayudar a que las galaxias vayan como transformándose morfológicamente. Así que no es solo ramp pressure.
Hi, Carlos Román, una bonita plática. ¿Podrías comentar sobre el gas ambiental caliente? ¿Qué tanto de ese es primordial y qué tanto de ese es resultado de la misma evolución de los cúmulos?
El intracluster medium, me imagino que te refieres. Ok, otra muy buena pregunta. A ver si lo consigo rapidito. No, bueno. El gas que llena el espacio entre las galaxias en los cúmulos, que llamamos intercluster medium o gas intergaláctico, hay una componente que debe ser primordial, pero mucho de ese gas, las propiedades de ese gas, nos dice que viene de material extraído de galaxias que caen. De hecho, se conecta con la formación de medusas, porque ¿a dónde va todo ese gas que le quitas a las galaxias? Una de las formas de ver eso es la metalicidad, por ejemplo. ¿Cuál es la metalicidad del gas? Y esto, la gente que estudia intercluster light se dedica a entender el origen esencialmente de ese gas, y nosotros creemos que una gran componente de ese gas viene de galaxias stripped, ya sea hidrodinámicamente o también destrozadas por gravitacionalmente.
Tenemos tiempo para una última preguntita. Creo que ya tiene el micrófono.
Hola. Yara, quería preguntarte qué podés decirnos de los truncation radius, porque seguro tenés información de eso.
Sí, a ver si consigo una imagen. Aquí tal vez. Como la presión hidrodinámica actúa de afuera hacia adentro en la galaxia, nosotros, si no vemos las colas, lo que podemos ver es qué tan grande es el disco de gas. Si tú tienes una galaxia aislada, esperas que el disco de gas sea mucho más grande que el disco estelar. Mientras más le remueves gas, ese disco se va a ir achicando, 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 y el disco estelar se queda igual. Entonces, el cociente entre el disco de gas y el disco estelar te puede decir en qué etapa estás del stripping. Y nosotros hemos usado ese truncation radius, de hecho, para estimar cuánto ramp pressure ha sufrido la galaxia. Y de hecho, por ejemplo, las galaxias que ya pasaron pericentro, típicamente tienen un truncation radius, o sea, como chiquitito, un disco de gas chiquitito comparado con las estrellas. Así que sí, es un parámetro súper importante.
Última preguntita por aquí.
Quick question. Is there a difference in the fraction of AGNs from the galaxies that fall face on and edge on the cluster?
That's a very good question. We don't have the statistics. If you remember the plot I showed about AGN, the first paper was with 7 galaxies. So it was like the kind of discovery paper. Since then, we've been trying to put that number up, and there's a paper in preparation by a postdoc of mine where he's using Galaxy Zoo and many other things to try to do this with a large sample. We haven't looked at orientations, but I think it's a good idea to check. But the thing is that the AGN is such a small scale that I'm not too sure if the phase-on and edge-on is going to affect too much, because we think that magnetic fields are actually the ones helping to put it all in there. Thank you.
Okay, so let's thank Yara. And the next speaker in this session this morning is Aldo Rodriguez-Puebla, who's visiting us from the Instituto de Astronomía de la Universidad Nacional Autónoma de México. He's going to be also talking to us about evolution of galaxies, so we give the floor to Aldo.
Ok, buenos días. Muchas gracias a los organizadores por darme la oportunidad de presentar este trabajo. Que este trabajo es una forma de entender cómo se forman y evolucionan las galaxias desde una perspectiva estadística y empírica. Y espero poderlos convencer de que este tipo de estadísticas este tipo de herramientas estadísticas son bastante poderosas para entender la formación y evolución de galaxias. Okay. I'm going to switch to English, and I'm Aldo Rodriguez-Puebla, and these are the collaborators. These are my collaborators. Oops. Okay. These are my collaborators that I've been developed this model. Okay, so the goal is to understand galaxy formation and evolution, and we have two ways to do this. We have the empirical way, in which we can use observations to understand how galaxies form. So we have this method this method called the fossil record method, in which we use the spectrum of the galaxy to understand the stellar population in the galaxy and how the galaxy evolved. We have another way to do this, which is the galaxy population method, in which we use the statistics and the demographics of the galaxies as the galaxy stellar mass function, or the relation between the star formation rate and the stellar mass. So in these two approaches, we can understand how galaxies form in a very empirical way, but there is not a cosmological context to this. We have another method, which is a theoretical approach, and we use a structure formation model. So Yara already told us about the lambda CDM and how the dark matter forms and develops all this cosmic web structure. So we can use this model, the lambda CDM model, to fit with physics, with the physics that we know, in order to understand how galaxies form. The problem is that physics is very complicated, and we have two ways to approach this. We have the semi-analytic models. We use phenomenological rules in order to understand how galaxies form and evolve. Or we have hydro simulations, which are very expensive, and we can put all the physics that we know, all the hydro, all the gravitational physics that we know. But again, those are very expensive, and they are limited by the resolution. Now, we have a third method, which takes the best from the two worlds. We fed this third method with the demographic of the galaxies and the structure formation model to understand in an empirical way how galaxies form. So we take the best from these two worlds in order to build a model that is consistent with observations and with the cosmological structure formation model. This is really key, because then we can project observations into a direct interpretable cosmological framework to understand how galaxies form and evolve. One of the simplest techniques to do this is the subhalo-abundance matching, in which we take the galaxy stellar mass function, particularly the cumulative galaxy stellar mass function, which is shown here in blue. So we are plotting the cumulative galaxy stellar mass function as a function of the stellar mass. This is the galaxy stellar mass function, and we compare to the cumulative halo mass function. Now, what we ask is, what if what if the cumulative number of galaxies is equal to the cumulative number of dark matter halos? This will tell us that the probability of having this galaxy in this halo is the same. So we look for the mass, the stellar mass of the galaxy, and then look for the halo mass, and we can create this stellar to halo mass ratio as a function of halo mass. And we can, in a very empirical way, to understand how galaxies are populating galaxies and dark matter halos. So we have this ratio that we look here. By the way, this peak of the stellar to halo mass ratio is around 10 to the 12, which is the halo mass of the Milky Way, or very similar to the halo mass of the Milky Way. Here is a summary of what is the status of this stellar to halo mass ratio as a function of the halo mass. So we now understand that this stellar to halo mass ratio, which has been inferred through very different types of techniques, are very consistent between each other. We have very sophisticated techniques, we have very simple techniques, such as like the abundance matching, or sophisticated techniques as the empirical modeling, and all of them have shown this very consistent picture within the systematics of the stellar masses. Right? Now, what is interesting is that we can fit simulations with this stellar to halo mass ratio and try to see what are the predictions from this model. What I'm showing here is the two-point correlation function model, which is the probability of finding galaxy pairs, the excess of probability of finding galaxy pairs compared to a Poissonian distribution. And we see here the correlation function in different stellar mass bins. The circles are from observations, the SDSS, and the solid lines are the predictions from this model. Look that this very simple model predicts in a very nice way the observations. This is not put into the model, but it's a prediction. We have also predictions with environment. So here we are showing the luminosity functions and the stellar mass function as a function of the environment. So we are essentially measuring the number of galaxies inside of a sphere of 8 megaparsecs. We are going from environments that are very of low density, such as voids, or to very high density environment like the center of the clusters. Here, compare the shaded areas with the circles and see that the shaded areas, which are the results from the galaxy halo connection, it's very consistent with the observations, which are the circles. We have also comparisons with the abundance of galaxies in groups, which are the analogous of the mass functions, but as a function of the halo mass of the groups. And also this model seems to be in a very nice agreement with the observations. Now, everything that I have said does not distinguish between different types of galaxies. The main property in the main assumption of this model is that stellar mass is everything. The stellar mass is defining everything in these models. Now, there are a new generation of galaxy halo connection models in which try to understand how galaxies with different properties are hosted by by halos of different type of properties. So let me introduce you this paper that is in preparation, which is a code that we are calling Empire, and try to understand how galaxy properties and dark matter halo properties are connected within each other, but not also the galaxy properties, but also the supermassive black holes. The idea of this type of codes is that you use dark matter simulations in which you know the properties of the dark matter halos in a very accurate way. So you can look into some region of the dark matter simulation, extract the dark matter halo, and see how is the assembly history of that dark matter halo. So we can do it for any halo of the simulation and ask the question, how does this merger tree that we are seeing here, this assembly history of the dark matter halo, translate into the assembly history of a galaxy? So what in Empire we are doing is that there is a very nice correlation between the clustering properties of the halos and their age. So what we are plotting here is the maximum circular velocity of the dark matter halo versus its halo mass. Now, the color code is showing the age of the dark matter halo. You see that redder color, the older the galaxy. So for a given halo mass, the dark matter halos that have larger maximum circular velocity will be older. Now, also, that is related with the environment of that galaxy, of that dark matter halo. So redder older halos will be more clustered than younger halos. Now, this is telling us something that is very similar to what Yara was telling us during her talk. So we would like to assign older halos to older galaxies. Okay, and this is what we do. So we use this diagram as a diagnostic diagram to assign quiescent galaxies and star-forming galaxies to dark matter halo. I'm not going to enter into the details here, but you can ask me later during the question session. But also, we have that galaxies, and as Yara pointed out, suffer environmental processes. We are doing this in a very simple way, saying that the galaxies that suffer a central quenching, that is the nature scenario, suffer an extra quenching process due to their environment, we choose the nurture. Okay, so the idea of Empire is to have different assembly histories for star forming and quiescent galaxies, and we can put also different properties of the galaxies within these merger trees. So we have also galaxy sizes, and essentially we are assuming that the potential of the dark matter halo will be proportional to the potential of the galaxy, and that will give us a recipe for connecting the size of the galaxy with the potential of the halo. I'm skipping the details, and just telling you also that we have a way to put supermassive black holes by using the definition of radius of influence into the dark matter halos. Okay, I'll go very quickly because I'm running out of the time. So I will also tell you that we have different ways to put supermassive black holes in this model. We have at least two flavors in this model. What is that is in an AGN that is in a radiative mode, and another type of supermassive black holes that are more in a quiescent mode. Okay, so this is essentially the summary of the galaxy-halo connection in our model. So we have the theory, which starts from the point of embodied simulations. We fed these embodied simulations with various recipes to address different galaxy properties, and then feed with some observables that will represent the universe. So here are some observational constraints, which are the evolution of the galaxy stellar mass function from redshift 0 to redshift 10, the evolution of the quiescent galaxy stellar mass function, the fraction of central galaxies, the specific star formation rate, which is the star formation rate divided by the stellar mass as a function of stellar mass for star forming and quiescent galaxies, and its evolution from redshift 0.1 to redshift around 9. We have also the cosmic star formation rate based on ultraviolet and far infrared. We have also far infrared luminosity functions, which Vladimir Avila will tell more about this in the next session. The evolution of the ultraviolet luminosity function, the size-mass relation for star forming and quiescent galaxies, and also the quasar luminosity function, and the black hole to stellar mass relation at redshift 0. All these constraints have been used in order to constrain the model, and the model has been fed into embodied simulations. So here are some preliminary key results, in which we have the stellar to halo mass relation. We can say that from redshift 0 to redshift 10, this has evolved very little. We have also, and we know that there is some physics behind this stellar to halo mass relation, or stellar to halo mass ratio, and essentially at low redshifts, stellar evolution is doing the job of shaping this relation, and at high masses, the AGNs are doing the job for shaping this relation. But what is more important, and I will spend a bit more here, is that with these models, we can infer how galaxies are evolving across the time. So here we have the different types of galaxies that we see at redshift 0. And we can plot the tracks, the evolutionary tracks of these galaxies as a function of time. So you can see here that for a big elliptical, this white line, we can see how these galaxies assemble as a function of time, but we have also color code what has been the star formation history of these galaxies. We see that most of these galaxies have very high star formation rate between redshift 2 or redshift 3. They have the highest star formation rate, and we can read off for the next galaxies. Now, this dashed line in the next following slides will show the demarcation line between star forming, statistically being star forming, and quiescent galaxies. This is for the stellar to halo mass ratio, which is the efficiency of galaxy formation. And this is happening between galaxies of 10 to the 10 to 10 to the 11. This is the infrared luminosity function, in which we also see that the elliptical galaxies were the most dusty galaxies in the past. And we also see the ratio of the stellar to size ratio, and we see that elliptical galaxies were really compact in the past, and now they have increased their size, perhaps due to minor mergers. We have also seen the black hole to stellar mass ratio, in which also, again, the most massive galaxies had the largest ratio in the past for the compared to the low redshift counterparts. Now, I'm going to skip this because I'm running out of the time. Just tell very briefly that if we compare the clustering of the galaxies as a function of the main sequence, these kind of models are it's very interesting that they reproduce the 2-point correlation function. So essentially we are seeing here the clustering as a function of the distance to the main sequence. These are the highest star-forming galaxies, star-forming main sequence galaxies. This is the below the main sequence, the Green Valley and the quiescent galaxies. And you can see here the comparisons to the SDSS. Just essentially focus with the black solid line and the black and the gray circles. This is for the previous one was for central galaxies. This is for satellite galaxies, and you can see that the model is reproducing most of these properties. And I will give here my I'm good. And I will give you with my summary and conclusions.
Okay, so you actually ended up early, so we have plenty of time for questions. Are there any questions, preguntas?
Hello, good morning. Thank you for your talk, Aldo. This is Doris Topaja. I would like to ask if you can give us more detail on the new version of your model. You said something dividing into quiescent and star forming. Could you comment on that, please?
Right. So, yeah, thank you very much for that question. Right. So, as I said, if we color code this diagram, so in the y-axis we are plotting the maximum circular velocity. So here I didn't explain it in too much detail, but I can say it now. So what I'm plotting here is the maximum circular velocity, but this is the highest maximum circular velocity along the history of the dark matter halo. And we are doing the same here, but for halo mass. So for a given halo mass, you see that galaxies with the largest B peak are the oldest galaxies. They have the largest redshift and assembly redshift history. So and also we see that these are the more cluster galaxies. So what we would like to do is that the galaxies with the largest B peak will be the most quiescent galaxies. So for us, this the B peak is translated into a probability of being quiescent. The largest the B peak, the more quiescent the galaxy. So this is what this diagram is trying to do. So what we are assigning to the largest BP galaxies is a more probability of being quiescent. And on the other way around, galaxies with the lowest BP will be the most star-forming galaxy. Now, let me add that there is some randomness that we add to that number as well.
Okay, we have another question over here.
Okay, I have a very, very nice results, interesting. I have a question about your star formation encoded redshift versus stellar mass plot. Maybe you can skip back to this. Yeah, I think the previous one, exactly. So there is a stochasticity about 10 to the 11, about the dashed line there. Can you speak to that? Because I think this would be very interesting to, evaluate with recent surveys what Yara has presented. We have our own surveys going on, and the stochasticity has probably something to do. Okay, I have a hunch, but I would like to hear your opinion first.
So perhaps you cannot see that stochasticity here, because in the way that this plot is constructed is that, so we are following thousands of dark matter halos or millions of dark matter halos. If we are taking the average, we are taking the average assembly histories of all those halos.
It's actually worse.
Right. So and we are actually plotting here the star formation rate average of all those halos. But there is actually some stochasticity in those star formation histories. So we will have that some galaxies. So if we can extract one of the assembly histories of those galaxies, you will see that the star formation history is doing something like this, reflecting in some way the formation, the cosmic web formation structure. But also there is some randomness, because you will expect that local processes in the galaxy is created the stars, right? So we had also that.
Did you look into this? Like,
yeah,
any principal component that correlates with these?
Right. So in a 2016 paper, we showed that the accretion, if you plot the dispersion of the accretion of dark matter halos, give you slightly the correct number for the for the width of the star forming main sequence, and you needed something more, which comes from the stochasticity of the local processes of the star formation.
Let's talk later. I think.
Right.
Gracias. Tengo una pregunta. Sí. No recuerdo el volumen de la simulación que estás, pero igual en este tipo de plot que estabas mostrando recién, de la evolución de las distintas propiedades, sí, a ver qué volumen, 250 megaparsec.
Son dos simulaciones, una de 250 y una de 20 megaparsec.
Bien. Bueno, igual en estos gráficos que mostrabas la evolución de distintas propiedades, y conectando un poco con la charla anterior, ¿esto es en promedio en toda la simulación o estudiaste cómo es esa evolución en distintos ambientes? Porque por lo que veíamos en la charla anterior, es diferente la evolución en distintos ambientes.
Right. So I will come back to this plot. So what I described, what the people here asked. So the way that we are assuming whether the galaxy is quiescent or star forming, that was just for a central galaxy. Now we have an extra parameter that we are actually tuning with observations. That is essentially an environmental parameter. So the plot that Yara showed, the famous paint plot, tells you that these two are orthogonal essentially. So for central galaxies, you have that this kind of internal processes are the ones that are shaping the evolution of the galaxy. Now, if you are a central galaxy, in addition to that central quenching, if you can say it like that, you have an extra parameter, which is an environmental quenching. So we are doing it that way. It's a very simplified model, but it seems to work, because if we look to the correlation functions, when you look into the correlation functions of satellite galaxies, you can see here that the model is, oh, sorry. You can see here that the model, as you decrease in the distance to the main sequence, is reproducing nicely the correlation function of satellite galaxies, of quenched satellite galaxies. I don't know if that answered your questions.
So, so the plot you were showing about the evolution were about the central galaxy. I didn't get that. It
Right.
was the central galaxy.
It was for central galaxies, but we are adding an extra
Yeah, I
parameter
understand, but
to satellite galaxies.
thanks.
Okay, so let's thank Aldo, please.